This is the fourth video in the geomagnetism section, and in this one I'll talk about particulars of rock magnetism and how rocks can record magnetic field in Earth's past. Are you ready? Let's get going. Up to the learning goals. Now, first of all, I need to introduce some basic physics that have to do with the magnetic properties of materials, and the most important part of the basic physics is that all magnetic materials have unpaired electrons. And a class of elements that have unpaired electrons are the 3D transition metals. Then I'll talk about some minerals that contain the 3D transition metals and thus have strong magnetic properties. You'll need to understand the difference between paramagnetic and ferromagnetic behavior. And I'll introduce a concept of magnetic hysteresis, which will allow us to understand exactly how a material becomes magnetized. Finally, I'll talk about a set of different ways in which rocks contain remnant magnetization, or a record of the magnetic field at the time something happened. All of these remnant magnetizations are abbreviated as a letter RM for remnant magnetization. And examples of remnant magnetizations that you should understand are isothermal remnant magnetization, thermal remnant magnetization, depositional remnant magnetization, chemical remnant magnetization, and viscous remnant magnetization. Let's go. Some rock magnetism facts. First of all, we need unpaired electrons in materials. Now, why is that? Well, basically, electrons have an intrinsic magnetic moment. We call this magnetic property of an electron its spin. The second thing you need to remember from basic chemistry is that 2 electrons are allowed in each orbital level of an element. So within one orbital level, you can have a spin up and a spin down electron. Thus, if you have a completely filled orbital, there is no magnetic moment associated with that orbital. Only unfilled orbitals have a residual magnetic moment. Now, the transition metals turn out to be a particularly important class of elements to generate magnetic properties. And the transition metals in the 3D row are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. What happens as you go across the series is that we fill the 3D orbital levels according to Hund's rule. And what's Hund's rule? Well, Hund's rule is that first you fill each orbital level with a spin-up electron. Then after each orbital has exactly 1 electron, you go back and begin to fill all the orbitals with the second electron in the opposite spin direction. Let's look at this in terms of a schematic for orbital levels or energy levels of electrons. Now, in a free atom with no external fields, the d electrons might have all the same energy level. But once you put the element inside of a crystal structure, there are electrical fields acting on it that tend to remove the degeneracy of the electronic levels, so the d orbitals all have different energy levels, and I've schematically shown that with 5 steps here. Scandium has exactly 1 d electron, so we've put a single d electron in the lowest energy level with the spin pointing up. Titanium has 2 d electrons, and so it has 1 in the lowest level and 1 in the next level up. Then we go to vanadium with 3 d electrons, and we go up again to the next orbital level. Chromium then 1 level more, and finally manganese tops the scale here, and we have filled each of the d orbitals with one electron, each in the same spin-up direction. So as you can see here, manganese has 5 unpaired electrons, and so it has a potential for a magnetic response with those all 5 spin orbitals pointing in the same direction. The next element in the periodic table is iron with 6 d electrons, and there now we have no space for it in a higher level, so it has to go back and start filling from the bottom again, and it fills with a spin down. Thus, iron all by itself has 4 unpaired electrons and 1 orbital that is filled with 2 electrons. Then cobalt adds another electron, so cobalt has 3 unpaired electrons. Nickel has 2 unpaired electrons, copper has 1 unpaired electron, and zinc has no unpaired electrons, and thus has no magnetic properties. Now, something to think about is in oxides and silicates, iron is in the +2 valence, thus 2 of the electrons have been removed from iron in order to allow it to chemically react with oxides or silicates. So if iron is in the +2 state, how many unpaired electrons would it have? And finally, iron also can be in a +3 state, and I ask you again, how many unpaired electrons for Fe+3? Let's talk about the important magnetic minerals. Now, in general, the magnetic minerals are what are called opaques. And this comes about from petrologic examination of rocks, rocks being a collection of minerals, and most of the minerals are translucent. They allow some light through, so under a transmission microscope you can see a variety of colors and shapes of semi-transparent minerals. However, there are additional minerals in most rocks that completely block the light, and these minerals that block the light are often the oxides of the transition metals, and thus they are opaque to light and simply show up as black blebs under the microscope. Among these important minerals are the iron oxides, and common iron oxide is magnetite, which is Fe3O4, and Fe3O4 has iron in the +2 valence state. Hematite, another common iron oxide, is Fe2O3, and here iron is in the +3 valence state. In addition to the iron oxides, there are iron manganese oxides, iron titanium oxides, iron sulfides. You notice iron is ubiquitous. It's a very common element in all minerals, and thus iron-based minerals are a major source of magnetic properties of rocks. And finally, there are the iron, nickel, cobalt metallic alloys. So let's go on from there. 2 more terms to learn. Paramagnetism means that magnetic moments of a material align with external fields. Thus, you turn on a magnetic field and any internal unpaired electron immediately rotates around so that it is parallel to the applied magnetic field. Now, in the case of paramagnetism, as soon as you remove the external magnetic field, thermal agitation realigns all of the electrons. They begin to point in random directions and have no net magnetization. However, in some classes of materials, ferromagnetism is observed, and with ferromagnetism, the magnetic moments stay aligned in the absence of an external field. So you apply an external field, the electrons align themselves to the external field, you turn the field off, and there's something that holds the electrons and keeps them from reverting to their random distribution. Of course, permanent magnets need to be ferromagnetic. There are additional rock magnetic behaviors, diamagnetism and antiferromagnetism and so forth. We'll not consider those for the moment, and I want you to simply to keep in mind what paramagnetism and ferromagnetism are. Let's talk about magnetic hysteresis. And this gets at the heart of how a material holds on and displays its magnetic properties. I have over here a box, and in this box are arrows pointing in a distribution of directions. Think of those as electrons pointing in, with their spins pointing in random directions, or think of it as a collection of minerals. Each of these minerals has its magnetization pointing in a different direction. I introduce here a XY plot, and on the horizontal axis it says H applied. That's the magnetizing a field applied to the sample, and the vertical axis is the magnetization induced in the material. So we apply a magnetic field and measure how much magnetic induction there is, how much additional magnetic field as a result of the internal magnetic moments of the rock aligning themselves. So that arrow pointing down, short arrow pointing down, represents an external field applied to that box full of spins. Now, as a result of that external field, some of the spin orientations in the box rotate around and point in the direction of the applied field. Thus, the box, the rock, has an induced magnetic response. I can plot this on the graph. It's the curve started at the origin, no magnetic field applied, no induced magnetization. Now you see that as I've turned on the magnetic field, I've induced a magnetization in the rock, and thus there's a point at the end of that black curve. Now let's ask what happens if I increase the strength of the induced magnetic field, or the external magnetic field. Well, what do you think is going to happen? A stronger field is going to tend to cause those other arrows in the box to align themselves with the applied magnetic field. And thus there's an even stronger magnetic response of the box. Here I've filled in a curve of increasing magnetic external field and increasing induced magnetization. You notice it comes up and levels off. And it levels off at a level of induced magnetization that's called the saturation magnetization. Now, why is there a saturation magnetization? Well, it's pretty clear. Looking at the box, we've aligned all the internal magnetic moments. There are no more moments to align. Thus, the induced magnetization is as strong as it's going to get. Now, let's ask what happens if we start with a strong applied field and a induced magnetization, and we remove the field. Now, as we remove the field, those moments within the box, some of them will start agitating and realigning themselves, and there I've shown diagrammatically some of the arrows within the box going off into random direction, the result of which is that the induced magnetization in that box is smaller than it was. So here's a curve. It starts at the maximum saturation magnetization, it comes down the line, and then when we're back at zero applied field, there is still some remaining magnetization. That amount of remaining magnetization is a remnant magnetization. The idea is we've applied a strong magnetic field. It has caused the internal magnetic moments to align themselves. We turn the field off, and at least some of those internal magnetic moments are locked into place and cannot revert to a random direction anymore. Okay, so we've magnetized the rock by applying a strong field to it. Now, what happens if we reverse the direction of the field? So instead of the magnetization pointing down, the magnetization is pointing up. Well, I'll step over to this side, and show you now that, well, the box now aligns itself going in the new direction, the magnetic field, and the curve comes down and shows a saturation magnetization in the opposite direction. So we've applied a field in the other direction, and we've gotten a magnetization in the reverse direction. Okay, now we can reduce the magnetic field back to zero. The magnetization goes back to a remnant magnetization with some of the magnetic moments locked into the direction that was applied and some of them becoming randomized again. At this point, we have a remnant magnetization in the negative direction. Finally, if we apply a strong magnetic field again, we can go back to a strong saturation remnant magnetization in the original direction. So overall, this curve is called a magnetic hysteresis loop, and we have used application of a strong magnetic field to obtain an isothermal remnant magnetization. And we abbreviate that as IRM. Now let's talk about thermal remnant magnetization. Imagine a volcanic rock emerging from an edifice and flowing down the side of the mountain. As it cools from the melt, it hardens into a crystal. The crystal contains minerals, opaque minerals, the oxides of iron, that can be permanently magnetized. However, at high temperature, those minerals are paramagnetic. Their magnetic moments can flip around and point in the direction of an external magnetic field, Earth's magnetic field. So they align themselves with Earth's magnetic field. As the rock cools farther, it will become ferromagnetic below a Curie temperature. So above the Curie temperature, the minerals are paramagnetic. Below the Curie temperature, the minerals are ferromagnetic. Ferromagnetic minerals can have a permanent magnetization. They can be magnetized in the absence of an external field. So at that point, the Earth's magnetic field direction has been locked into the rock. Well, there's one more complication to that there is yet another temperature called the blocking temperature, and to get a stable magnetization that persists for geologic time, you need to drop the rock below its blocking temperature. And under those conditions, then this remnant magnetization obtained by cooling through the Curie temperature gets locked in and remains for millions of years. Generally, having a high Curie temperature is good. The higher the Curie temperature, the more stable the magnetization is. For example, magnetite has a Curie temperature of 580 degrees centigrade. So ambient conditions of around 20 degrees C are much, much colder than its Curie temperature, and its blocking temperature is a few hundred degrees below its Curie temperatures. So magnetite remains stably magnetized for a long time. In contrast, a hydroxated iron compound like goethite, which is common rust, has a Curie temperature of only 120 degrees centigrade and a blocking temperature significantly lower than that. Thus, goethite will not maintain a magnetization over a long period of time. It is easily remagnetized by other magnetic fields. So here's the picture to take away. A volcano, erupting lava, the lava flowing down the sides of the volcano, each flow building up from the oldest to the youngest at the top. As the volcano continues to erupt, Earth's magnetic field may be changing. So one flow may record an Earth's magnetic field in the normal polarity, and a flow below that may have cooled through the Curie temperature at a time in which Earth's magnetic field was reversed. Thus, the volcano has a stratigraphy through time, layering through time, of different magnetizations as Earth's magnetic field has cooled. And one can come to the volcano and sample rocks of different ages through the layers and reconstruct Earth's magnetic field at the location of the volcano. Now, depositional remnant magnetization is a different process, and here we imagine magnetic minerals like magnetite eroding out of rocks, igneous rocks somewhere, being carried by streams and rivers into oceans or into quiet lakes. These magnetic minerals initially are suspended if they are small enough, and as they're suspended, they will tend to align themselves with Earth's magnetic field, just as a compass needle will align itself with Earth's magnetic field. As these particles settle into the sediment at the bottom of the ocean or the bottom of the lake, they can remain aligned in the direction of Earth's magnetic field, and thus the sedimentary rock preserves the orientation of Earth's magnetic field at the time the sediments were laid down. So here's a picture demonstrating that idea. You see Earth's magnetic field coming into the ocean there, and here you see a fairly shallow inclination. So the magnetic particles floating in the ocean are aligning themselves parallel to Earth's magnetic field, and then coming down and being laid down in the sediment, preserving that orientation. There are secondary remnant magnetizations, the primary ones being thermal remnant magnetization and depositional remnant magnetization. Secondary means it's hopefully weaker or it's not as useful, and let me point out what secondary remnants are. Well, first of all, there's the isothermal remnant magnetization that I already talked about when I talked about magnetic hysteresis. You use a strong magnetic field to align the magnetization of the minerals in the rock. An example of this in nature would be lightning strikes on rock outcrops. The strong currents generate strong magnetic fields, which can realign the magnetization of the rocks. And thus, one has to have care in selecting rocks to do paleomagnetic studies. You don't want to sample rocks that have had their magnetization reset by a lightning strike. There's chemical remnant magnetization. The idea here is that as new minerals precipitate out of solutions in a chemical processing of the rock, they can obtain a remnant magnetization at the time the minerals formed rather than at the time the rock was originally created. So chemical remnants could be a confusion on top of, or an overprint on top of a primary magnetization associated with the original formation of the rock. Then there's viscous remnant magnetization, which occurs by just simply long exposure to a magnetic field. So unlike isothermal remnants, where you apply a very strong field for a short period of time to change the magnetization, a weaker field applied for a very long period of time can change the magnetization of the more weakly magnetized minerals within a rock. Now, viscous remnant magnetization actually can be cleaned. It is a noise that sits on top of primary magnetization, and paleomagnetic researchers have determined ways to identify viscous remnants and to remove them from their samples. So that brings to the end my discussion of the basics of rock magnetism. Coming up, we have to look at the marine and continental paleomagnetic record.